And we are back for the 5th anticipatory briefing. Welcome to our live audience. Please come forward. You still have 30 seconds to take a seat. The first rows are available, except for the two first ones because of the cameras. Thank you very much for being with us. Also, hello to our online viewers joining us today through the magics of the internet. So we are going to dive into a fascinating topic, mixing robotics, artificial intelligence, and also biocomputing, neuromorphic engineering, and a lot of very complicated words I will have to say for the next few minutes. So our next speaker is a senior tenured researcher at the Italian Institute of Technology. She studies how we can apply neuromorphic engineering approaches to the design of robotic platforms to enable the creation of autonomous machines. The title of her talk is Embodied Neuromorphic Intelligence. Please help me welcome Chiara Bartolozzi.
Thanks. Wow, such a nice introduction. I'll try to do my best. I can't see you, so I'll try to do my best to kind of explain the keywords that were mentioned during the introduction. If you don't understand, you can also interrupt me, because I really want you to understand what we do. I'm here for this reason, so don't feel shy if you want to interrupt. So, I don't know. Next. Okay. Well, this is, I don't know if I have to explain it, but we are in the unconventional computing, the small dot in the inside of the circle. And why we do unconventional computing? Well, let's start with the nicest slide of the talk. I'm showing you animals. From a small cute squirrel to a bee, because the idea in the research that we do that we call neuromorphic engineering and computation is to look at animals and try to understand why animals are so good at doing certain things with such small brains, with only very few and small energy consumption. So an animal can, or we can, go around the world, find food, find mates, and exhibit very complex behavior and intelligence, what we call intelligence. And we can do that with a chocolate bar, right? We don't need huge power supplies attached to us. And this is something that robots cannot do. And so the idea is to understand how comes that the computation that is performed by animals in their brains is so much better than what we have in current technologies. We are witnessing this hype about, or these very great results from artificial intelligence, but this has a huge cost in terms of power consumption, of computational resources, and we have huge data centers connected to power plants, basically. So the research here is really going back and trying to understand how brain computes, and from there design new type of technology that can go closer to our capabilities with a lower power budget. We don't do that for general purpose computation. We are not going to design the new computers that can do anything, but this type of approach is valuable in those problems that we solve, that as other animals solve, that is interacting with the real environment in the world and accomplish a task. It's not about the high precision computing. That's not something we want to solve with this system. So a lot of it, this is kind of the single technical slide of this talk. What we can do is to look at which are the characteristics of digital computation, so the computation that you have in your laptops, in your phones, in the big data centers, and what is instead characteristic of neural computation. And you can compare the two. In the digital computing domain, you have largely serial computation. Even though now we have GPUs with a lot of parallel computation, the idea is still that you have operations that you do in a sequence, one after the other. While in the neural populations, you have very high degree of parallelisms, a lot of neurons that interact with each other in a recurrent way. So the flow of information doesn't go only step by step forward, but also goes back and lateral. And there are a lot of connections between neurons. And so it's performed in a very different way. The variables that we use in digital are zeros and ones. You have switches that turn on and off. And with that, you use these as building blocks to compute a mathematical equation, for example. While in the neural systems, the variables are analog. They are molecules that move from one side to the other of the neuron so that they create changes in how the neurons react to communication that arise from other neurons. And so we have to use and combine computational primitives that are far beyond zeros and ones. Digital is based on transistors, and transistors are very fast computing elements that are very precise. You have zeros and ones. The downside is that one transistor fails, the full system fails. Neurons and synapses that are the main components of neural systems are very slow, imprecise, we would say stochastic computing elements. Nevertheless, the computation that we do, that our brains do, is very reliable and is very precise. We, do what we need to do at the precise time we need to do that, most of the times, and reliably. Another big difference is that in traditional computing, you have, on one side, the CPU, that is a central processing unit that does the operations, and on another side, you have a memory. And you have to take data from the memory, bring those data to the central computing unit, and do the computation, and then bring that the data back, the result of the computation back. This is where your energy is wasted. While in the brain, you have neurons and synapses that are connected, and the information is in the connectivity between these neurons and synapses. And so what we say is that brains do in-memory computing. The memory is co-located with the computing elements, and so you don't have this back and forth of data that costs a lot. Another very big difference that is really related to tasks that robots have to do, for example, is how we acquire sensory information. This is kind of the basic of everything. You wouldn't be able to do anything if you don't receive information from the external world, if you don't see something, if you don't touch something. Now, traditional robots, your cameras in the smartphone, so on, they just take snapshots. They take pictures that have nothing to do with what happens in the external world. If you look at a white wall, you keep taking pictures of a white wall. That's a waste. What our senses do, they react through different physical mechanisms to changes. So if you have something moving on top of the white wall, then your photoreceptors get active, send messages to the brain only when there is something that is changing. And this is important because you capture the information when there's something meaningful, and you don't send data around when this is not needed. So this is kind of one of the main big results that we have now in the neuromorphic engineering domain is to have what we call event-driven neuromorphic sensors. So sensors that work similarly to our sensory systems. And we have vision sensors that now, for example, are produced also by Sony, so by big companies that are starting investing in this domain. And given you have, and we also work on other sensory modalities. I personally work a lot on tactile systems for the robots. And this is how you acquire the information, changes how you have to process the information and how easy it would be to extract what is relevant to guide my behavior or the behavior of an artificial system. Another big difference that we start looking into now is that artificial intelligence nowadays is mostly disembodied. It's in a computer. It doesn't have a body that interacts with the external world. And this changes a lot, because if I have a body and I act, I can change how I acquire information. I can, pick up an object. Let's say I have an object here. I pick it up, and I can rotate it. I can feel it, and depending on how I move it, I can increase the information that I get from the object. Our artificial intelligence systems, they don't have this. They don't have this connection between how you can move something to acquire information. And this can simplify, for example, the problem of perception. That is a very difficult problem. It's not easy at all, even if to you it feels natural. So I was asked, so kind of this is overall what we do. To do so, the field started in the late 80s in Caltech, and it was a collaboration between biologists that were studying the brain and circuit designers, using the first transistors. Now the field is much bigger than that, and it's really interdisciplinary. So this is kind of a list of the different disciplines that revolve around this topic and that are needed to progress. So to give you an idea, we need people looking into microelectronics, because that's what we do, right? So the big thing here is not having an algorithm, but also designing the hardware that can support that algorithm that is different from the traditional transistors used as zeros and ones. So we need microelectronics, and we also need people doing physics and materials. And this is because, for example, there are these new devices that are the memoristic devices that can store a memory and can function as elements that store how the connectivity between different neurons should be. And this is to learn something, to have a system that is capable of learning. And this can be integrated directly in the computing devices, so we have this possibility of doing in-memory computation. We also need materials, for example, for the interface with the external world. Something that we started to do is to look at embodied intelligence. So not only the intelligence that comes from neurons, how they are connected, how they process sensory information, but also the intelligence that comes from the body, from how the sensors are integrated on the body, how the materials that are used by the robots, for example, to interact physically with the objects, like soft materials that cover the tactile sensors, they start pre-processing the information. How they are distributed in the body is meaningful. We have in our fingers a very high number of tactile receptors. We have very high spatial resolution in the fingertips. We have a much lower resolution in the back because we don't need that. And if we have the same resolution all over our body, then we have so many neurons and so much information to process that we need a brain that would be very big, a head that would be very big, and it's not sustainable. The same happens for the eyes. Our eyes, they don't have constant resolution as traditional cameras. They have a fovea, where you have a lot of receptors that can see a very small, fraction of what we perceive as the visual space at very high spatial resolution. And we need to constantly move our eyes to move the fovea and focus on what is interesting to us, what is a face that I want to recognize. But then I need to move the eyes so that I use my peripheral vision that is very low resolution just to move the eyes and find interesting things that I can process in more details. This is an amazing way to save resources, to save the number of neurons, the number of receptors, the size of the eye and the size of the head, and the energy you would need to process all the data and to maintain this system alive. So I think, I don't know, I'm very excited by all these things. And so we started talking with people doing soft robotics and morphological computation, because I think that the materials and the design of the robots and the intelligence that is in the body should talk to the intelligence that we build with the neural systems, with neuromorphic engineering. So I think here I went to the long-term thing that should be in the next slides. We need neuroscience, we need people telling us how the brain works. And we start from neurons and synapses. Now there's dendritic computation, so that really goes beyond the general abstraction that we use in computation now when we try to implement neuromorphic. We need software engineering and computer science for the theories of computation. And of course, everybody that works in the application domain, in robotics, in biomedical engineering, we can have, I will say in a couple of minutes, which are the applications beyond robotics where we can use neuromorphic engineering, where it would make sense to work in neuromorphic engineering, and ethics. Wherever we talk about intelligence, we also need to have experts in ethics that tell us what happens when we have this intelligence integrated in artificial systems. So where we are now, I think I will not go into all these things that are written here, but I wanted to show you a video. Will it start automatically? Or shall I? No. How can I make the video play? So we have now basically proof of concepts. As I said, we have the technology is mature for the event-driven vision sensors. So what you see here is a humanoid robot that is called the iCub. It's a robotic platform that has been built thanks to the a big contribution of the European Commission through different collaborative projects, where we wanted to build a platform that could be a common platform to researchers doing research in humanoid robotics, and especially in how the cognitive capabilities of robots can be learned and built through the interaction of the robot with the environment. iCub is a cub, so it's a...
What I propose is that you move on to the next point.
Okay.
And we'll figure out the video, and in 5 minutes, we'll show it when we're ready. Si on peut faire ça en régie, si vous pouvez trouver une façon de la diffuser dans quelques minutes. Et comme ça, just move on and we'll watch it.
Okay.
So keep the content for now. I'm sure we can find a way to show a video.
Okay,
somehow.
So basically what we have are proof of concepts. Now you will see the video there with the robot following a target, basically. we have also proof of concepts in other applications. That's, for example, in the domain of health. So there are amazing papers now on people who use tactile sensors that behave similarly to the tactile sensors that we have in our hands, that are integrated on hand prosthetics or foot prosthetics and can give feedback to a user. And this is amazing because imagine you have an active prosthetic device you cannot feel. If you don't feel your hand, the device is not part of your body. And it's very difficult to accept and to control. And the cognitive load in controlling such prosthetic devices is very high, because not to crash things when you close your hand around, for example, a plastic glass, you need to use vision. So you really need to concentrate and pick up the thing and make sure it doesn't fall down, make sure you don't squeeze it too much. If you have instead tactile feedback, well, this is easier. And also, there's a sense of ownership. So we are there at the first steps. It's not all integrated. There's still a lot of work to be done, but using a neuromorphic type of encoding, like the same sensory encoding in the tactile sensors, gives a more natural feeling to the prosthetic user when they give tactile feedback. Also, since these systems have low power and you can design small circuits, we are going towards wearable devices that can monitor what a user is doing and can so inform an artificial system that needs to collaborate with the person. So I'm talking about physical human-robot interaction. I'm talking about when a rehabilitation device is used, like an exoskeleton, for example, to improve the physical interaction with the patient. Or I'm talking about simply medical devices that monitor your physiological state and inform your doctor. This can be done all locally with extreme edge computation, so that we don't have transfer data to big data centers. And this is important for privacy, because if I can keep my data local, I don't have risks of people using this data or taking this data. I'm not an expert in cybersecurity, so this is something someone else is doing, but I'm told that this is important. So I don't know, if do we want to...
Can we find the video online? Because there seems to be a problem with that Microsoft technology handling the slides. Could we is Microsoft a sponsor? If it is, I apologize. Can we find a video on YouTube? So maybe we could...
There are tons of videos on YouTube. I don't know if you want to do it now.
I mean, if you give us the name of the video, they can find it, and then they can set it up, and then I can ask you a few questions, and then maybe we just see 1 minute of the video. I think it's interesting.
There could be a YouTube. This is not something I'm doing, but it's my PhD students that do that. There should be a YouTube channel somewhere.
Okay.
Try with EDPR, but I don't know how easy that would be to find it online.
It's a vague search term.
Yes, exactly. I have my laptop, so if you're interested after the talk, I can show
Sophie is backstage trying to figure out something, but I think we can go to questions, if it's okay with you?
Yeah.
And then we will look at the video. So thank you very much for the presentation. I think it's a concept I heard under another name, which was biomimicry, the idea of kind of mimicking the way nature works in machines. It's very interesting. So please send your questions through the app. I'm going to relay them to the stage, and Sophie hopefully can work her magic and put them into the communication system with me. You finished the talk, you mentioned how you could use sensors and give robots and machines kind of sensory abilities. But at the beginning, you showed this something that I understood as a technology that could allow us to kind of have animals do what we want. I was wondering if it would work with my children.
With your children?
Yeah. Could I control them? Could I reprogram my children so that they behave? No?
Do you think I wouldn't have done that?
I thought I saw hope for my sleeping patterns. Like, hey, here maybe I could just like upgrade their software. Basically, you mentioned that this computing paradigm has very specific properties. It's low consumption. It's not maybe as precise. It's more, in a way, alive. How do you see, we live in a world of binary computers. Now we hear a lot about quantum computing. There's big advances in that. And then this form of organic computing or biocomputing. We had a presentation on that also yesterday.
On organoids,
yesterday afternoon with another speaker. How do you see these three kind of paradigms living together, and what does what? In what case do you go with a traditional computer? In what case is that going to be the answer?
So there's there are a lot of different interesting things. As you said, quantum computing. I was visiting a university in the Netherlands where I met a person doing quantum computing. And to me, it's really a different word. It's very difficult to understand. And I think a key point here is translation. So what I did during the PhD and even later was really to translate the language between engineering and neuroscience and finding a common understanding. This is the main thing in our interdisciplinary work. Finding, using the same word with different meanings. It creates so much confusion, but that's what happens most of the time. So we start, talking with quantum people because they say, oh no, we can do neuromorphic. And so we try to do this exercise in trying to understand what would be neuromorphic there. Could we use a quantum system to implement computation that is inspired on the brain? We are mostly, I'm kind of old, I feel so old. I'm old school. I use transistors on silicon because that's a very well-known technology. That we can use. We know the physical principles and how they work, and we can map neuroscience in there. We are starting to move to different technologies, like, for example, still using transistors, but on flexible materials, using organic that allow to print the circuits, to have something flexible that you can wrap around the body. That could be a robot, but could also be a person, or a soft robot, because they have flexible things. And then we can go beyond. There are people that use photonics. It's written in that slide. There are people working with organoids that.
But my question is, quantum seems to be very good at cracking very intense math problems, right? So it's great for encrypting, decrypting, stuff like that. The regular computers we have around us, we know their limitation. They're quite time-consuming, energy-consuming. They're very good at certain tasks, but you need to specialize them very carefully. It's what a company like ST Microelectronics, which is French and Italian, does all the time. You go to them and they build a chip for the specific idea of your car, needing like computer vision, whatever. Organic, what kind of problem will it solve? It's going to be this kind of sensory problems that you need in a system, and you have very low energy consumption. You need like long-term autonomy. I'm trying to understand where it fits in the overall picture, among the different technologies.
Yes, I think we need to find where each technology can shine, can give the best results. As you said, quantum computing is for certain applications. What I said at the beginning of my talk is neuromorphic computing, at least I don't see it as delivering a general purpose computer, but delivering a computer that can make sense of, imprecise, noisy, ever-changing information from the sensors and be able to, generate meaningful behavior.
Which is a huge thing, which computers cannot do now. And so it's a huge market, it's a huge opportunity behind, if you can do that, right?
Definitely,
Yeah.
yeah. It would give, I mean, now deep learning can do vision partially, right? Can solve some problems.
At a very high cost, right?
Exactly.
It takes a child seeing 2 cats to know what a cat is. It takes a computer 5 billion pictures to understand what a cat is.
They are replicating mostly what happens through evolution and development rather than what happens in a brain of a kid that is learning, because in that brain there's already something that comes from, ages of evolution that created an infrastructure. And so, for example, if we can understand how a brain is built from DNA, from the instructions that you have in the DNA, and on, also based on how the neurons evolve in the embryo, and we understand these rules, we can then design something using this know-how without starting from a tabula rasa and tons of data that are biased, that are...
So it's kind of the missing piece of computing a little bit. It's like where the current capabilities stop, is this kind of the intelligence you're describing. It's going to replace something like a mechanical Turk, the Amazon system, where you can connect to a computer system, then humans do the task and it comes back. And the tagline is artificial intelligence. Think about it. It's a very good one. We have the questions coming in. Thank you for sending them through the app. The first one is, we lack people who could take care of our children and grandparents. When do you think empathetic robots will be ready to provide these services in an accessible, cheap, mainstream way?
I've been asked this question for ages now because, it's one of the big challenges. It also poses a lot of ethical questions. We are moving a lot that path. The robot that you see in these slides that is now not
Can
working.
we see la vidéo? Est-ce qu'on peut mettre la vidéo sans son peut-être pendant qu'elle parle? We'll see. Maybe it comes. Maybe the whole thing has crashed actually for 20 minutes. We don't know. Maybe.
I just wanted to say that this robot here is a research platform. Okay, it's very complex. You can only use in a lab. It's not safe to have this around a person. But all the technologies that we study on this would be the former director of my institute used to say, this is the Ferrari of robots. You don't give a Ferrari to a person driving in the street, but he used all the know-how that is developed there and plug it into something that is lower cost, that is safer, that is easier to use from a non-expert. We are moving there. There's a lot to do, and I think we need to include all these technologies like neuromorphic, like soft, to go in that direction. Softmax, the robot of the... it was a cartoon. That was the robot, the big one that was hugging people for health. It was soft. It was
There's actually
harmless.
a project from Italy, I think it's called Paro, and it's a seal. Have you seen that? They use it for dementia patients. It's actually a 15-year-old project. It's a seal. So it has the fur, it looks like a seal, and they give it to patients with dementia, and they immediately get like
a pet robot.
Like a pet. But it's full of fur. It really looks like it's a project from Italy. I think I saw it a while ago. So it really has potential. And it's a huge problem in countries like Japan or Korea, where you have like elder populations and no workers. But this is going to happen, according to you, right? That there's going to be caring robots to do specific things.
Yes, this is one of the driving factors in the robotic community to keep working on robots, because the idea is to design robots that are useful, and there's a big problem in caregivers. Right?
Yeah, exactly.
And I feel that also there's also a big gender issue there, and if you can deploy a robot that can help, I think now we are going towards something that is not completely autonomous, but can, share and collaborate with humans.
One of the things also that's interesting, we talk about robots, is that in our mind, the robot, it looks like it's like anthropomorphic, it's a human. And actually, there's a lot of robots happening, but they're like red lights or, things that we don't...
A Roomba.
Yeah, Roombas, exactly. And so in the care system, for example, there are robots for injections or robot to put you in your bed or lift you from your bed, and that don't really look like robots, but there's going to be a lot of automation.
We also have
that.
Surgical robots,
exactly,
right?
Yeah.
Or robots. I have a colleague who's working for robots that are looking at how to insert a needle in newborns. It's very, very difficult to insert a needle in newborns, and it's painful, and you need really very well-trained people, and it can take ages, while he has this robot that looks at bioimpedance to find the vessel. And this is a robot, it's not a humanoid.
Exactly.
The humanoid has the advantage that if it's not creepy, this is kind of a creepy one because it has a mask now. It was for moving the lips for human-robot interaction, but if you can find the right unthreatening, not uncanny robot, for example, for elderlies, it would be easier to create a connection.
Yes.
Right? And there are a lot of people, psychologists and engineers that look into this.
You mentioned ethics. It's obviously a big question, ethics. What does the army do with that type of research? It's obviously, you've seen animals being used in conflicts. For example, dolphins are used for mine or attack. Do you see that technology being used in that context also? Like
it is. There are drones. There are the big dog from Boston Dynamics.
Yeah.
And to me, it's very difficult because
it's very difficult. But every technology
I don't want to think that technology that I develop can be used to harm people. And most of the times, it's about defending. But there's a very, very thin line between the different concepts. It's something, for example, we don't do that. We never look into military applications, but it's also true that a lot of funding can come from there.
Yeah, definitely. Always something that's
if you can use a robot to
science and
if you can use robots to remove mines from landfills, I would consider that as a plus.
So, the title of the session is We're Trying to Anticipate. So what we want our audience to walk away with is a sense of, when this topic is mentioned, they understand how potentially it will impact them on a personal level, but also on their job, their work, their companies, if they work in the private sector, and also in terms of the regulation, how politicians, how the framework around us is going to evolve. What do you think we should prepare for on an individual level? We should prepare for in the next 20, 25 years to have machines around us that have capabilities that are more alive or more human. That's what we should expect.
I think that what we are trying to develop now, I can tell you, for example, we spoke about different possible applications in healthcare, in robot companions, military. I think there are others. We are trying to write proposals right now to develop systems that can be biodegradable and can act to monitor the environment. And, for example, by monitoring in agriculture, if, for example, very simple, if the soil is humid enough, you don't water that part of your land, but you put water only where the soil is dry, and this would save the water consumption. I think that now we are looking into these type of systems that can automatize or improve the use of resources and energy, and more having these, systems that would be ubiquitous in our smart cities. It's strange because some technology is there, but then you don't see it in use. So I think we should kind of try to better use what we have, the technology that we already have, to improve life of people. In some parts of of the world, this is done. In some parts, it's just not, and it's difficult to understand why. As a scientist, we have this, why don't we use it? And we see that there's a waste of resources all over the place. Then I think these robots that would be more alive, more sentient, or
more distributed,
conscious.
Apparently.
I would say we would have a lot of robots with a lot of specific tasks that you wouldn't even perceive as robots, because they are not humanoids or animals that you can recognize as an artificial agent.
So bad news you get the second question, like, should we prepare to become lazy because we would subcontract our duties to robots? That's not gonna happen.
If I can ease my daily tasks as caregiver, for example, we mentioned the Roomba, or the washing machines. Guys, it was a revolution for women to have a washing machine, so they didn't have to wash by hands, and they could do something different, more interesting, less dull. And if I don't have to think about vacuum cleaning my place, wow, that's great.
So it's not replacing, it's kind of taking us to more interesting tasks, right?
To me, yes. It's, of course, there is a question there. So we keep saying there will be different types of jobs, right? The big fear is robots are going to steal jobs. It's going to happen that some tasks are going to be substituted, but that's first we are ready. We know, and we can be prepared to that, rather than that happens and nobody does nothing to kind of allow people who were doing those works into finding something different, into relocating and reinventing themselves. Not everybody will be able to do that, so we need also...
But you made a very subtle difference, but it's not replacing jobs, it's replacing tasks. So every job has multiple tasks, and the most boring, simple ones are going to be replaced, freeing us time for us to be creative and do management, etc. So it's destroying occupations, not jobs. And there's new jobs appearing all the time, actually. At least that's what history tells us. The last question we want to finish now so that people can go to the other session. If I'm the regulator right now, if I'm a government, like, what should I do about this? Should I put some laws that say, like, the army is not allowed to look at it? Or, like, what should we do? Quickly, 1 minute. What's your advice? How do I regulate this field, or how do we deal with it as policymakers?
I don't know. So I would say that from what I do, there's still a lot of basic research being done.
It's still too early to kind of understand what's at stake.
Yeah, I think before regulation, we need to understand each other. And there should be, as I said before, translation work where we create a common understanding to understand, which are really the capabilities of these systems.
This is what Yann Lequin of Meta said. It's like before regulating AI, you think that before inventing the safety belt, you had to invent the car. And so you still have to, it's the same story. Thank you very much. Please give a warm round of applause to Chiara Bartolozzi. Thank you, Chiara.